succeed, to see if I believe they're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now. Swear to God, man, I'ma make it soon. Silence all the haters as they see us making moves. I do what I want, so I got nothing to prove. Staying motivated, teaching others what to do. I'm staying focused, my mind is open. They start to notice that I'm in motion. There is no potion, you're not just chosen. It takes devotion to stay composed, man. Never stop, there ain't no time to fall. Try to live, get it up, you got one life to ball. Thinking big, never small, cause you gotta want it all. When you finally get that call, you get ready, take it on. Need a hand out, I already stand out. Starting to advance now, ready to expand now. You don't have a chance now, cause we're in demand now. Make it by the grand now, feeling in command now. They're looking right at me to see if I succeed, to see if I believe they're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now. I have a dream, that's all I need. I'll make it happen with some work and belief. Know what I want, so I'll take it on. I've made mistakes, but mistakes make you strong. Let's break it down for a minute. I want the crown, I'm gon' get it. You hear me loud, man, I'm winning. Yeah, Charlie Sheen will be grinning. These ladies know that I'm sinning, and this is just the beginning. I'm closing in the ninth inning. There ain't no point in resisting. Living life like a dream, live it right, that's the thing. Every night got a team, I've been tied to the scene. Out on stage, here I'm screaming. Okay, it's a dream, and I pray as a team. One day it'll be me. If I want it, then I get it. Head down, don't regret it. Push myself to the limit. If I play it, then I win it. I'm just saying, I'm just living for today. For a minute, I don't stay, I just visit. Have no shame, I admit it. Looking right at me to see if I succeed, to see if I believe they're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now. Swear to God, man, I'ma make it soon. Silence all the haters as they see us making moves. I do what I want, so I got nothing to prove. Staying motivated, teaching others what to do. I'm staying focused, my mind is open. They start to notice that I'm in motion. There is no potion, you're not just chosen. It takes devotion to stay composed, man. Never stop, there ain't no time to fall. Try to live, get it up, you got one life to ball. Thinking big, never small, cause you gotta want it all. When you finally get that call, you get ready, take it on. Need a hand out, I already stand out, starting to advance now, ready to expand now. You don't have a chance now, cause we're in demand now. Make it by the grand now, feeling in command now. They're looking right at me to see if I succeed, to see if I believe. They're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now.
Hello, hello. Yeah.
Go. All right, everybody. Stacks. A stack is a LIFO data structure. LIFO is an acronym for last in, first out. This allows us to store objects into a sort of vertical tower, like a stack of books or a stack of CDs. We use the push method to add objects to the top of the stack, and the pop method to remove objects from the top. So here's a real-life example of us creating a stack data structure. After declaring our stack, we can add objects to our stack. The objects that we'll be adding are various video games. To add an object to our stack, to access objects on the bottom of our stack, we first need to pop or remove objects from the top of our stack. If I need to access Minecraft on the bottom, we'll pass in a string, the name of a video game. Let's add Minecraft first. Then let's add Skyrim. Then Doom. You can pick your own games if you want. I don't care. Then Borderlands. And then Final Fantasy VII. FFVII. Okay, let's check to see if our stack is empty now. So let's move this line of code to the bottom. And run it. So our stack is no longer empty. This returns false. So with the stack, we can at least take a look at the items within the stack without removing them. So let's use system.out.println, and I will print my stack. So this will print all of the objects within my stack, beginning with Minecraft, then Skyrim, Doom, Borderlands, and Final Fantasy VII. However, by printing our stack, we're not removing items from the stack, so that's completely fine. So this time, let's pop the topmost item from our stack by using the pop method, stack.pop. And we don't need to list an object, because pop will always remove the topmost object from our stack. So now Final Fantasy will be missing from the top of our stack. So if I was to repeat this again, well then this will remove Borderlands, and then Doom, then Skyrim, and then lastly, Minecraft. Then if you pop again, this is what happens. An exception. Empty stack exception, so that's something to keep in mind. Now, when you pop the topmost object from a stack, this will actually return that object. If you need the object from the top of the stack, you can pop it and then assign it to something. So let's say string my fave game equals stack.pop, and then I will print my fave game. And this will print Final Fantasy VII. And it should be missing from the top of my stack if I was to print my stack. So Final Fantasy VII is no longer in my stack because I popped it, then assigned it to the string variable of my favorite game. So in order to take the topmost object from a stack, you use pop and then assign it to something. If you ever need to take a look at what the topmost object is within your stack, you do not want to use pop because that will remove it. You can instead use the peek method of stacks. So what I'll do is system.out.println stack.peek, and then immediately follow this with printing my stack. So let's run this. So the topmost item within my stack after using the peek method is Final Fantasy VII. Then after printing my stack, Final Fantasy VII is still at the top of my stack. So if you ever need to take a look at the object that is at the top of the stack, without removing it, you can simply use the peek method. If you need to search for an object within the stack, you can use the search method. Let's print stack.search, and we pass in our object as an argument. So the very first item in a stack will have a position of 1. You would think it's 0, but it's actually 1. Now let's find Borderlands. That will be in position 2 from the top. Then Doom would be, of course, 3, Skyrim is 4, then Minecraft is 5. So if you search for an item that is not within the stack, like Fallout 76, well then this will return -1. If search does not find this object within your stack, it will return -1. So with stack, we can actually run out of memory. So let's add like 1 billion copies of Fallout 76. We find Bethesda's warehouse of unsold Fallout 76 games. So we'll create a stack of 1 billion copies of Fallout 76. We can do this using a for loop. Int I equals 0 as long as I is less than like 1 billion. That's probably close enough. Increment I, then we will push a copy of Fallout 76 to our stack. So stack.push Fallout 76. And this is what happens.
A few moments later.
So we will run into an out of memory error due to the Java heap space. So it is possible to run out of memory when adding objects to our stack. Now, this is an interesting feature that may or may not happen to you if you add 1 billion copies of Skyrim onto a stack. Damn it, Todd Howard, you did it again! Redo features in text editors, like when we go to edit, then undo typing, or redo typing. We can move back or forward through browser history by hitting the back or forward button in the top left corner of most web browsers. We can implement them in backtracking algorithms if we need to navigate a maze or search through file directories. And another is that we use them when calling functions. Whenever we call a function, we add what is known as a frame to the call stack, but I'll probably save this topic for another video. So in conclusion, everybody, a stack is a LIFO data structure, last in, first out. It stores objects into a sort of vertical tower, a stack of objects. You use the push method to add objects to the top, and the pop method to remove objects from the top. So those are stack data structures. In the next video, we'll be covering queues, which work a little bit different. So if you can, give this video a thumbs up and drop a random comment down below. But yeah, that is a stack data structure in, well, computer science.
The biggest AI competition in India has already started. Are you ready to stand out with the Langful?
What's going on, everybody? It's your bro. Hope you're doing well. In this video, I'm going to explain queues in computer science. So sit back, relax, and enjoy the show. If you find this video helpful, please remember to... Oh, hey, we're talking about queues today. So queues are a FIFO data structure, not to be confused with FIFA. FIFO as in first in, first out. An example would be a line of people. It's first come, first serve. Whoever's there first gets helped first. So this is a collection designed for holding elements prior to processing. It's a linear data structure. Here's an example. Imagine that we're a cashier and we're selling tickets to a concert. We will help whoever approaches our register first. It's first come, first serve. In other words, it's FIFO. First in, first out. Unfortunately, a wild Karen appears and she would like to talk to the manager. Now, Karen is going to waste everybody's time, so it's going to be a while. In the meantime, Chad enters the line. He will enter in at the back and wait his turn, followed by Steve and then Harold. So Karen is at the head of our queue, our line, and Harold is all the way at the back, our tail. As you can see, Harold is very anxious right now. Once Karen has been defeated, Chad will move to the head of our queue. So Chad will now be helped next, and Harold will still be at the tail until somebody else enters the line. Once Chad has been helped, he will move out of our queue, and Steve is at the head now, and the tail will move as well. And then once Steve has been helped, Harold is the only one currently waiting in line for his tickets. He will be at both the head and the tail of our queue. So that's kind of how a queue works. It's first come, first serve, FIFO, first in, first out. If you were here first, then you will be helped first. Now, the concepts of adding and removing objects from a queue are known as both enqueuing and dequeuing. Enqueuing is the concept of adding an object to the end of our queue, our tail, and dequeuing is when we remove an object from the head of our queue. Now, what methods do you need to enqueue and dequeue from a queue? Well, it really depends on the programming language that you're working with. A lot of you voted for data structures and algorithms using Java, so I'll probably stick with Java then. Here's an example. Now, to enqueue and dequeue, we need, well, a queue. So let's create one. Queue. Then we need to list the data type of the objects that we're going to add to this queue. Let's work with strings because strings are objects and they're fairly simple. And I will name this queue queue equals new. Now check this out. I will attempt to create a queue object and instantiate it, and the data type is string, and I will add a constructor. Now we cannot instantiate the type queue. Here's the reason why. So if we take a look at the queue class right here, queue is actually an interface and not a class, and based on our lesson on interfaces, we cannot create an instance of an interface. An interface is meant to be more of like a template that we can apply to another class. So to utilize queue technology, we need a class that implements queue. Now, taking a look at our Java collections hierarchy, there are two classes that implement queues, one of which is the linked list, and the other is the priority queue. Now, priority queues, they will rearrange their elements based on a certain priority, so they wouldn't be a good example. So to utilize the features of a queue, we are going to create a linked list because we cannot instantiate a queue itself because it's an interface. With that being said, let's change equals new queue to equals new linked list. We won't be focusing on any of the features of linked lists. We'll save that for another video, maybe the next one. I haven't decided yet. So we will only cover the features that linked lists will utilize via the queue interface. Now, with the queue interface, there are three methods that we inherit from the collections parent class: add, remove, and element. These will do approximately the same thing as enqueuing, dequeuing, and peeking at the topmost element. However, they throw exceptions, and according to the documentation, it's actually better to use this column of methods instead. These will return a special value. We have offer, which will enqueue or add an element to the tail of our queue. Poll will dequeue. It will remove the head of our current queue. And then there is also peek. It will not remove the head, but it will examine it and return it. So those are the three dedicated methods that we implement via the queue interface. There are some additional methods too, which we'll cover later, which we inherit from the collections class. So let's begin by offering a bunch of people to our queue. This is how we enqueue or add elements to our queue. So first in our line, we have Karen. So to add her to the queue, we would type the name of our queue, queue.offer. And we will offer Karen to the front of our queue, and she would like to complain to the manager. Next, we have Chad, queue.offer Chad. Then we have Steve, And lastly, Herald. Okay, now if we were to display our queue, we'll place it within a print line statement. We will pass in queue as an argument, and this should display our queue in order. First, we have Karen at the head, then Chad, Steve, then Harold at the tail. One method that we implement from the queue interface is the peek method. We can use the peek method to examine and take a look at the object at the head of our queue. We're not actually going to remove the object at the head of the queue, but take a look at it. So within a print line statement, I will use queue.peek method. And after peeking over our cash register, unfortunately, Karen is at the front of the line. Now to dequeue, we can use the pull method. So type queue.pull, and this will dequeue your queue. So Karen is no longer at the head of our queue. So let's pull a couple more times for practice. So after pulling twice, Karen and Chad are now gone. Using pull a third time, we'll remove Steve, and lastly, Harold. Now, the nice thing about the pull method is that it will not cause an exception. According to the Java documentation, you can use element to peek, but it will throw an exception. So if I was to use element at the end, this would cause an exception then. So usually it's preferable to use this column of methods, even though they're similar. These will not throw exceptions: offer, pull, and peek. Now with queues, there are some additional methods that you might be interested in. The queue class will extend the collection class, so the queue class inherits everything that the collection class has. And there's some pretty useful methods within here. I'll show you a few. So the first is that we can check to see if our queue is empty. So within a print line statement, I will type queue.isEmpty. And if our queue is empty, this will return true. So if I move this line of code after we offer a bunch of strings, a bunch of people to our queue, if we check to see if our queue is empty, that will be false. There are people currently within our line. So that is the isEmpty method. We can also check to see the size of our queue. How long is our line? System.out.println queue.size. And the size of our line, our queue, is 4 objects. We have 4 people waiting in line to be helped. So that is the size method. And another is the contains method. We can check to see if our queue has a certain object that we're looking for. So within a print line statement, I will type queue dot contains and then pass in an object. Let's check to see if Harold is at the back of the line. He's been waiting here patiently. Queue dot contains Harold. And according to the contains method, Harold is in fact within our line. That is true. However, this method does not give the index the position in which Harold is in. Imagine that we yell out, "Hey, Harold, are you there?" And he yells back, "Yeah," or "True." That's kind of how the contains method works. So these are three useful methods that queues inherit from the collection class. Now, where could queues be useful? They're actually used in quite a number of things, but here's a few examples that came to mind. So one, they can be used in keyboard buffers. Have you ever typed so fast that the computer couldn't render all of the characters onto the screen? And all of those characters were added to a buffer. They were all displayed in sequence, and they were waiting for their turn to be displayed. So with a keyboard buffer, letters should appear on the screen in the order that they're pressed, right? First in, first out. They're also used in printer queues. Print jobs should be completed in order. So we would start with page 1, then page 2, and just follow that pattern. And as we discussed before, they're used in linked lists, priority queues, as well as breadth first search algorithms. Well, everybody, in conclusion, a queue is a FIFO data structure. First in, processing. To enqueue, that means to add an element to the tail of our queue to the end. We can use the offer method in Java. To dequeue, we would use that is asked to speak with your computer.
It's 9:15. How am I already underwater?
I'm in the same boat.
I'm in an actual boat.
I thought Grammarly just fixed grammar. They make boats now?
It's more of a metaphorical boat.
Science. Hey everybody, it's your bro, hope you're doing well, and in this video we're going to discuss priority queues in computer science. So sit back, relax, and so first in, first out. However, a major difference with priority queues is that before we start polling and serving elements, we put them in some sort of order. Higher priority elements are served first before GPAs. Doubles, some GPAs, is queue, and we are going to insert some doubles, some GPAs. I'll name this queue equals new. Now queues are actually interfaces and we can't implement them directly, so we need to use a class that utilizes the queue interface. One that I know of is a linked list. Then finish instantiating it. Now to add add data to a queue, we use the offer method. Queue.offer, and then pass in a GPA. Let's make sure that these are not in order. How about a 3.0? Then the next student has a, let's say, 2.5. Then a 4.0, 1.5, and 2.0. Okay, now let's display the elements of our queue. One easy way in which we can do that is to use a while loop. And this is our condition. We'll continue this while not logical operator queue dot is empty method. While our queue is not empty, pull each element and display it. So within a print line statement, let's use queue dot pull to display and remove each element, beginning with the first one and then working our way to the end. So this will display the elements within my queue. So these are in first come, first serve order. Whatever element we were offered first, we are serving that element first. If an element was added last, well then it's served last. So that's a standard queue. Now with a priority queue, we're going to arrange them in some sort of order before we actually pull these elements. So let's change our linked list to a priority queue and run this again, and let's take a look at the differences. Okay, these are all in order now. So if we're working with numbers like doubles, these are arranged in ascending order, beginning with the smallest element. Let's pretend that these are grade point averages, GPAs. Why might we want to put these in order? Let's say whatever student performed the worst gets 2 hours of free tutoring, whichever student performed second worst gets 1 hour of free tutoring, and third gets half an hour of free tutoring. Now, if you need these in descending order, well, there's one change that we're going to make. Within the constructor, we can pass in a comparator, but that's a little advanced for us and we haven't discussed that yet. So there is a default comparator that we can use found within collections. Collections.reverse order method. So these elements will be in reverse order then. In this example, let's say that whichever student has the best GPA will receive, I don't know, a gold medal, like the Olympics. And the second best student will receive a silver medal, then a bronze medal. And then every student after that, I guess, will receive nothing. But that's okay though, they got some free tutoring in the last example. Okay, now let's change the data type. Let's say that these are now strings. And let's put these in standard order. So let's change these to strings. Maybe this student has a B, this one has a C, A, F, and what are we missing? D. If we have a priority queue of strings, well then these elements will be in alphabetical order. So if we need these in reverse alphabetical order, again we can pass in a comparator, and then one that we can use is from collections. Collections. Reverse order. And these elements within our priority queue are now within reverse alphabetical order. So yeah, that's a priority queue. Think of it like a queue. However, we first sort these elements based on a certain priority. we will pull and serve the elements with the highest priorities first, and work our way to elements with lower priority. So yeah, that's a priority queue. If you would like a copy of this code, I'll post this to the comment section down below, and well, yeah, those are priority queues in computer science.
Run Windows, Linux, and more on your Mac with unmatched performance.
Hey, what's going on, everybody? It's your bro, hope you're doing well. In this video, we're going to discuss linked lists and computer science, so sit back, relax, and enjoy the show. Now, before we dive straight into linked lists, we're going to take a closer examination of arrays and array lists. We will see what disadvantages that these data structures have, where linked lists excel at, so we'll compare and contrast the differences between the two. With what we understand with arrays and array lists, these data structures store elements in contiguous memory locations. In this demonstration, I'm storing letters of the alphabet. Suppose that the first element of my array has a memory address of 123 Fake Street. Obviously, these are not real memory addresses, but this is how I like to think about things. If this was a memory address, then the next element in my array may have an address of 125 Fake Street, then 127 Fake Street, 129 Fake Street, and then you just continue on in that pattern. Now, arrays are fantastic at randomly accessing elements because they have an index, but they're not so great at inserting or deleting elements, especially when those elements are closer to the beginning of the array. Here's an example. Suppose I need to insert a new element at index 3. Since this element is already occupied with a value, I would need to shift my elements to the right in order to accommodate room for this new element. So the process of shifting is cumbersome. But once this element is empty, then I can insert a new value. So it's not that big of a deal if I have a small data set, but imagine if I had 1 million elements. I will need to shift my data up to that many times depending on the location of the insertion. And the same concept applies with deletion as well. We would shift our elements to the left to close the gap. You're probably thinking, dude, why are you talking about arrays in a video about linked lists? Well, where arrays have difficulty inserting and deleting, linked lists actually have the advantage. Here's a representation of a linked list. A linked list is made up of a long chain of nodes. Each node contains two parts, some data that we need to store, and an address to the next node in line, also referred to as a pointer. Linked lists do not have an index the same way that arrays do, but each node contains an address to where the next node is located. So these nodes are non-contiguous. They can really be anywhere within your computer's memory. If our initial node has a memory address of 123 Fake Street, like our array example, then the next node in our linked list could have a memory address of maybe 101 Help Boulevard, and another could be 404 Nowhere Lane, then 666 Crime Circle. Each node knows where the next node resides. I imagine this as if we're following a scavenger hunt or a series of clues to find the end of the linked list, the tail. Each node has an address, a clue as to where the next node is. We begin at the head and work our way towards the tail, following each clue, each memory address found in each node. Then we know when we reach the end of our linked list when we check that address, our pointer, and it has a value of null. That means we're at the tail, we're at the end of our linked list. Inserting a node is easy in a linked list. There's no shifting of elements involved. Wherever we need to place a new node, we take the address stored in the previous node and assign the address of our new node with the address from the previous node, so that our new node is pointing to the next node in line. Then we can take and replace the address in the previous node with an address that points to our new node. It's as simple as that, and we're completing our chain simply by inserting a node at a given location. There's only a few steps involved, no shifting of elements required. Deleting nodes are easy too. Wherever we need to delete a node, we have the previous node point instead to the next node in line. Again, no shifting of elements is necessary. Now, this is where linked lists tend to be inferior to arrays. They are bad at searching. We can randomly access an element of an array because we have an index. With a linked list, that is not the case. To locate an element, we need to begin at the head and work our way towards the tail until we find the element that we are looking for. This itself takes time. In fact, it would take linear time, but making the insertion or deletion of a node is constant. This variation of a linked list is a singly linked list. There are single links to each node. However, there's another variation called a doubly linked list. A doubly linked list requires even more memory to store 2 addresses in each node, not just one, which is the case with a singly linked list. One address for the next node and another for the previous node in our chain. The benefit of a doubly linked list is that we can traverse our doubly linked list from head to tail or from tail to head in reverse. Each node knows where the next and previous node is, but the downside is that a doubly linked list uses even more memory than a singly linked list. So how about we create a linked list in real life now? Let's do it. Alright, ladies and gentlemen, with all of that out of the way, let's create a linked list. Linked list lists the data type of the objects we'll be storing within this linked list, just strings because they're easy, and I will name this linked list linked list. Linked list equals new linked list. And to list the data type again, we are storing strings, add a constructor, boom, you got yourself a linked list. Now, if I was to take my cursor and hover over my linked list declaration, there's a note here that says, this is a doubly linked list. Each node knows where the previous and next nodes are. Now, if we head to the linked list class itself, there's a few things I need to mention here. Our linked list stores the memory location of our first and last nodes. These are effectively the head and the tail of our linked list. And there's also an inner class named node. Each node knows the memory address of the next and previous nodes within this linked list. Now, taking a look at our linked list class definition, our linked list class implements the deck interface, and a deck is more or less a double-ended queue. So with the deck interface, we implement 12 additional methods. So here's just a few of them. So we can add to the head, add to the tail, remove the head, remove the tail, peek at the head, peek at the tail. Some will throw exceptions, some will return a special value, so you can use any combination of these really. And not only do we have these 12 methods, but we can treat our linked list as either a stack or a queue. We can push, we can pop, we can pull, and we can offer. So just to demonstrate, let's first treat our linked list as a stack. So linked lists do have a push method as well, if we need to push an element onto our linked list as if it were a stack. So let's push the letter A, and then I will display my linked list with a printline statement. System.out.println, linked list, and of course we have the letter A. So let's push another letter onto our stack. What about B? So at the bottom of our linked list we have A, and then on top we have B. Let's add a couple more letters. Let's represent a typical grading scale. We have C, D, and F. A, B, C, D, F. Notice that I'm intentionally leaving out E. We're going to insert that later. So within our linked list that's behaving as a stack, we have F on top, then D, C, B, and A. So we also have access to a pop method as well. Linked list dot pop, and this will pop the top of my linked list. So F should no longer be here. It's D, C, B, and A. So we can treat a linked list as a stack. We can also treat it as a queue as well. And just to save some time, I'm going to copy these lines of code. To add an element to a queue, we do not use push, we use offer. So linked list dot offer. and we will keep the order. So I'm not going to pop it quite yet. So we have A, B, C, D, F. A is at the head, F is at the tail. And to remove the head of our queue, we do not use pop, we use pull. And A is no longer in here, we have B, C, D, F. So you can use a linked list to mimic a stack or a queue. Before we move on to the next section, so you use pull. And A is no longer in here, we have B, C, D, F. So you can use a linked list to mimic a stack or a queue. Before we move on to the next section, I'm going to get rid of this pull method. So we have a typical grading scale, A, B, C, D, F. Where linked lists are really good is the insertion and deletion of nodes. Let's say for this example, I need to add a node between D and F that contains the letter E. So that's really easy to do with the linked list. We would type the name of our linked list, dot add, list and index, like 4, and our object, E. And then to remove a node, we would type the name of our linked list, dot remove, then list the object, E. So E should no longer be within my linked list. So where linked lists tend to have an advantage over arrays and array lists is the insertion and deletion of nodes. However, there's one catch to this. With a linked list, we still need to traverse the entire linked list to find where we need to go. Unlike with arrays and array lists, there's no random access to a linked list. Searching for an element is fairly straightforward too. So within a printline statement, I'm going to use the index of method of a linked list. Linked list.index of, let's look for F. So that would be at index 4. And before we wrap things up here, so that would be at at index 4. And before we wrap things up here, here's a few methods related to linked lists that you might be interested in. We can peek at the head or the tail node of our linked list. So within a print line statement, I'm going to print linked list dot and then use the peek first method. So the first node within my linked list contains the letter A. So we can peek last as well. Linked list.peek last. And the last node of my linked list contains the letter F. We can add new nodes at the head or the tail of our linked list by using the add first method for the head. So maybe I need to add maybe 0, because I don't really know what comes before A in the alphabet, so 0 would be a good bet, I guess. Or we could add to the tail by using add last. And after F comes G. And we now have G at the tail of our linked list. We can remove first and remove last. You can also store them within a variable too. Let's say string first equals linked list dot remove first. Then to remove the last node, we could just use remove last. Then. And let's store this within a different variable, remove last. So yeah, those are a few useful methods related to linked lists. In conclusion, everybody, a linked list is a data structure that stores a series of nodes. Each node contains 2 parts, some data and an address. Nodes are stored in non-consecutive memory locations. Each node can be really anywhere within your computer's memory. And elements are linked via these pointers. They contain an address for where the next node is. We've discussed 2 varieties of linked lists, a singly linked list as well as a doubly linked list. With a singly linked list, each node is made up of 2 parts, some data and an address. To traverse a singly linked list, we would begin at the head node and use the address as a sort of clue to find where the next node is located within our computer's memory. With a doubly linked list, each node is made up of 3 parts, some data, and 2 addresses, one address for the next node, and another address for the previous node, and it behaves the same way. And to traverse a doubly linked list, we could begin at the head and work our way towards the tail, or we could begin at the tail and work our way towards the head, depending on which way is closer to where we need to be within our linked list. What are some of the advantages of a linked list? 1, they're a dynamic data structure. They can allocate needed memory while their program is currently running. 2, insertion and deletion of nodes is really easy. If you're familiar with big O notation, this would be in constant time. There's only a few steps regardless of the size of our dataset. And 3, there is no to low memory waste. What are some disadvantages? One, there is greater memory usage because we have to store an additional pointer. Each node also stores the address for where the next node is located, and even more so with a doubly linked list, this will use a lot more memory because we need 2 addresses for each node. Now, 2, there's no random access of elements within a linked list. To find an element, we need to begin at one end and work our way towards the other end. And 3, accessing and searching of elements is more time-consuming. This is done in linear time. This is where arrays and array lists have an advantage. Since they use indexing, they can randomly access an element of an array or an array list. With a linked list, we have to manually traverse the entire linked list to get to a particular index, since we don't have random access. Now, what are some uses of linked lists? One, they could implement stacks or queues. If you need a stack or queue for anything, you could also use a linked list. 2, maybe GPS navigation. So let's say you have a starting position and a final destination. Each step or stop along the way is kind of like a node, and if you need to take a detour, you can easily change, insert, or delete a node and recalculate how to get to your final destination. 3, what about a music playlist? So each song within a playlist might not necessarily be next to each other within your computer's memory. You want your playlist to follow a certain order of songs, so that could be another use of a linked list. So those are linked lists. If you would like a copy of all my notes here and my code, I will post this to the comment section down below. If you can, give this video a thumbs up, drop a random comment down below, and well, yeah, those are linked.
Hi, this is Shweta. Your name?
Prashansa.
Prashamsa. So regarding weight loss, this survey is going on. So nowadays we are seeing many weight loss clinics over in Hyderabad mainly. Okay, coming to the point, like is treatment better?
Linked lists. What the heck is a dynamic array? A dynamic array is an array with a resizable capacity. If we need extra room for elements, we can increase the capacity, which we cannot normally do with a standard, typical, fixed-size array. Dynamic arrays are also known as array lists in Java, vectors in C++, arrays in JavaScript, and lists in Python. Here's an example of a static array, and then we'll take a look at a dynamic array. A static array has a fixed capacity. We determine that capacity at compile time, and we can't change it later normally. In this example, I have a static array with a capacity of 6 elements and a size of 5 elements that are currently occupied. The last element is open, so it's null. Each element has a memory address. Obviously, these are not real memory addresses, but this is how I like to think about things. Imagine that all of these memory addresses are houses, and they're all next to each other. Now, accessing an element is easy because we have index numbers to work with. We can randomly access an element in O of 1 constant time. The size of our dataset doesn't matter. However, searching for a stored value still takes time because we need to begin at index 0 and iterate over our array until we reach our value, or the end in case we don't find it. This is done in O of n linear time. The larger the dataset, the time to finish will increase linearly. And in the case of inserting or deleting, that takes linear time unless done at the end. No shifting of elements is required. However, the closer we need to insert or delete to index 0, we need to shift all elements that follow in order to make room for insertion or close any gaps in the case of deletion. So if I need to insert a value at, let's say, index 0, I have to shift all elements to the right by 1 to make room for this insertion. And then we can insert a value, room insert, right over each is up. In this example, I have a static array with a capacity of 6 elements and a size of 5 elements that are currently occupied. The last element is open, so it's null. Each element has a memory address. Obviously, these are not real memory addresses, but this is how I like to think about things. Imagine that all of these memory addresses are houses, and they're all next to each other. Now, accessing an element is easy because we have index numbers to work with. We can randomly access an element in O of 1 constant time. The The size of our dataset doesn't matter. However, searching for a stored value still takes time because we need to begin at index 0 and iterate over our array until we reach our value or the end in case we don't find it. This is done in O of n linear time. The larger the dataset, the time to finish will increase linearly. And in the case of inserting or deleting, that takes linear time unless done at the end. No shifting of elements is required. However, the closer we need to insert or delete to index 0, we need to shift all elements that follow in order to make room for insertion or close any gaps in the case of deletion. So if I need to insert a value at, let's say, index 0, I have to shift all elements to the right by 1 to make room for this insertion. And then we can insert a value. Now, currently with our static array, we're at capacity. Our array is full. Our size is equal to our capacity. Then in the case of deleting an element, we need to shift all elements that follow after this index where we're making the deletion and shift everything once to the left. So that would look like this. And our size is back to 5, so there is one element that is open. A major disadvantage of static arrays is that they have a fixed capacity. We can't increase the capacity once the size of the elements reaches capacity. In this separate example, I have an array with a capacity of 5 elements and a size of 5 elements, and it's completely full. I can't increase the capacity because the next memory block contains, I don't know, pictures of cats or something. You do you, I guess. A dynamic array has its own inner static array with a fixed size. Once the inner static array of our dynamic array reaches capacity, our dynamic array will declare and instantiate a new array with an increased capacity. Usually the amount that we increase the capacity by really varies depending on the programming language. It's usually between 1.5 and 2. I just picked capacity times 2 for extra emphasis. So what we'll do now is copy the elements over to our new array, and these have different memory addresses than our original array. So that would look something like this. We now have a new array with double the capacity, but like I said, it really depends on the language that you're working with. It's usually between 1.5 and 2. This array has a size of 5 elements that are full and a total capacity of 10. Then if you need to shrink the capacity, like if you're not using a lot of elements, you can always just do the reverse process of what we did to increase it. Now, with this new inner array, the insertion and deletion of elements is really the same as a static array. So you just shift all the elements to the right by 1 to insert a new element, or shift all the elements to the left to delete an element. What are some of the advantages of dynamic arrays? 1, there is random access of elements. That is done in O of 1 constant time. We can randomly access an element by an index number and retrieve the value. 2, there is good locality of reference and data cache utilization. Because all of these memory addresses are contiguous, they're right next to each other. Unlike with linked lists, you have to jump around a lot because all of the memory addresses are kind of random. And 3, it's easy to insert and delete elements at the end because there's no shifting of elements required. And for the disadvantages, a dynamic array wastes more memory than a linked list because we need to increase the capacity to accommodate more elements if we need the extra room, and we may not necessarily need all of this extra room, so a dynamic array wastes more memory than a linked list. 2. Shifting of elements is time-consuming. The closer we need to insert or delete, closer to index 0, we have to shift all elements that follow afterwards to the right in case of an insertion or to the left in case of a deletion. And 3. Expanding or shrinking the array is time-consuming because we have to copy all of the elements over to a new array with a different capacity. And that's the basics of dynamic arrays. Let's create our own dynamic array for practice. Alright, welcome back. We're going to create our own dynamic array using Java. In the future, if you ever do need a dynamic array, you might as well just use an array list. According to the description, it's a resizable array implementation of the list interface, and it's pre-built, so you might as well use it. I thought we would create our own dynamic array just for learning purposes and practice. But let's take a look at the ArrayList class. Within this class, there are a few defined members. There's a default capacity set to 10. There are overloaded constructors within this ArrayList class. We can set our own initial capacity, or we can use the default by not passing in an initial. We can set our own 10. They're in this class, learning purposes and practice. But let's take a look at the ArrayList class. Within this class, there are a few defined members. There's a default capacity set to 10. There are overloaded constructors within this ArrayList class. We can set our own initial capacity, or we can use the default by not passing in an initial capacity. There is a size to keep track of how many elements are filled within our array list, and our array list does have its own inner static fixed size array. And if we ever need to expand the size of this array, we just copy the elements over to a new inner array. So let's begin. Let's create a new class named dynamic array, and I'll get rid of this. So file, new, class, and this will be named dynamic array. Then finish. Okay, let's declare a few members. Let's create int size, int capacity. This will be the initial capacity. I'll set this to 10, but feel free to pick whatever value that you want, as well as an array of objects named array. I will declare this, but not yet instantiate it. So you can make these private. However, I think that'll make our code a little more complex and difficult to understand, although it'd be more secure. I'm just going to use the default visibility for these members here. All right, let's create some overloaded constructors. So public dynamic array. And within here, we will instantiate a new fixed size array. This dot array equals new array of objects with a capacity of whatever capacity the default is. So it's going to be 10 by default. And we'll create an overloaded constructor just in case the user passes in their own capacity that they would like to set. So int capacity, this dot capacity equals whatever capacity that we pass in. Okay, let's instantiate a new dynamic array. Dynamic, make sure to spell it right, dynamic array, I'll call this dynamic array with a lowercase d equals new dynamic array. So I'm not going to pass in an initial capacity, and let's print whatever the capacity is of our dynamic array. Dynamic array dot capacity, and this should be 10. Okay, now let's pass in maybe a capacity of 5, and this should be 5. Yep, cool. So it seems like that works. All right, let's head back to our dynamic array and declare all of the methods that we'll need. Let's create an add method, public void add, and there will be one parameter of object data. Next method, insert, public void insert. The two parameters are int index object data. Okay, next method we have delete. Public void delete. There is one parameter of object data. Then we have search. Public int, we're going to return an index. Search.
నమస్తే అండి, నా పేరు శారద, మాది వరంగల్. 7 years ముందు
And we will need object data. And let's return -1 for now. Then we have private void grow to expand the size of our array. Private void shrink. Then we'll need an isEmpty method. Public, we will return a Boolean value, is empty. And we might as well fill this in right away because there's only one line. Return size is equal to 0. If our size is anything but 0, we will return false. And lastly, toString. Public string to string. And I need to type in something. I'm just going to return null for the time being until we return something. Okay, let's begin by filling in the add method. First, we'll want to check to see if we're at capacity. If our size is greater than or equal to our capacity, then we better call the grow method to expand the size of our array. So if there is room, we will take our array at index of size, that should be the end of our array, equals data. Then we will increase our size by 1. Now let's head all the way down to the toString method to display the elements of this array, and we just need to iterate over these. Let's declare a local variable of string, string, and I will set this equal to an empty string, and we will fill in the elements when we iterate over it. So let's iterate over the elements of our array. So let's create a for loop for int I equals 0, and then I will continue this for loop as long as I is less than our size. You can do capacity too if you want to see the entire array, but let's begin with size. I is less than size, and I will increment our index I by 1. So I'm going to take our string and append it. String plus equals our array at index of I, that's 1, I, plus maybe I'll add a comma, then a space. Then we should return our string. Okay, this isn't perfect yet, but let's at least test it. Let's head back to our main Java file and add a few elements to our array using the add method. So let's use the default capacity of 10, so we don't necessarily array, maybe string method, A, B, and C. Now let's format this and clean it up a little bit. Like I would like to get rid of the last comma here, and maybe enclose all of these elements within a set of square brackets. So this is what we can do within the toString method. So after the for loop, let's check to see if our string does not equal an empty string. If that is the case, if there are elements to display, let's take our string. Then I'm going to create a substring and get rid of these last two characters, the comma and the space. So string equals string.substring, and the length is going to be beginning at index 0, and I will continue this until string.length method minus 2. Then after running this one more time, the comma and space at the end should no longer be there because we created a substring to end at the last element. Then let's enclose all of these elements within a set of square brackets. So I'll use some string concatenation. So I'll add a left square bracket, and then at the end add a right square bracket. And then these should be within square brackets now, and that looks a lot better. Now, what if our string is empty? Let's we will substance and size colon specs of size. Now let's begin deleting elements. So I will type dynamic arrays. That's array. You might. I think this like the dynamic array.
I knew I was underwater. I just didn't realize I was this underwater.
Doing well, and in this video we're going to run some tests on both array lists and linked lists in Java. So sit back, relax, and enjoy the show. Alright, let's begin. We'll need both a linked list and an array list. So, linked list, the data type will be integers, and I will name this linked list equals new linked list. Again, the data type is integer, add a constructor, boom, we got ourselves a linked list. And now we'll need an array list. Change linked to array. This will be named array list. Make sure to pay attention to the capitalization. Equals new array list. And we'll need to keep track of the time. We'll need a start time, end time, and elapsed time. And these will be of the long data type. We'll be working with nanoseconds, so a long is preferable to an int. A long is really just a really long integer. Think of it that way. So we have start time, end time, and elapsed time. Okay, and now we'll need to populate both our linked list and our array list, and we can do that with a for loop. We'll need a large sample size, maybe 1 million elements. That'll be good. So int I equals 0. We'll continue this as long as I is less than a million. And I believe that's about a million. Yeah, we're good. Okay, then increment I by 1 during each iteration. So I'm going to add I to both my linked list and my array list. So we can add primitives because Java has an autoboxing feature. So even though these are integer objects, we can still add primitives. And be sure to add to our array list as well. So arraylist.add I. Okay, let's move on. Now we'll keep track of the time. We'll need to assign the start time of value and end time of value before and after our operation. So let's say that start time system dot nano time method. And let's take a look. So this returns the current value of the running Java virtual machine's time source in nanoseconds. So we will get the start time after we do something. I'll just add a note here. Do something. Then we will get the end time. So end time equals system.nanotime method. And to calculate the elapsed time, that will be elapsed time equals display the link. Let's do that. System.out dot println, and let's say linked list. I'll add a tab too. Plus elapsed time plus ns for nanoseconds. And let's just run this to test it. So this portion of code really took, right between here, took 400 nanoseconds. Okay, let's actually do something now. So let's get the first element within our linked list. Linked list dot get 0. And let's see how long this takes. Okay, 13,200 nanoseconds. Now, with an array list, let's copy everything that we have for our linked list and change linked list to array list. And be sure to do that. That here as well. Array, list. And let's compare these. So we are getting the index of 0 for both our linked list and array list, and we will compare them. And it appears that our array list is slightly faster. Our linked list took 11,800 nanoseconds, and our array list took 6,700. So it looks like getting the first element of our linked list is going to be a little bit slower than our array list. Turn this 100,000, so that's right in the middle, and do the same thing with array list as well. So array list dot get 500,000, and let's see how long this takes. Okay, so our linked list took way longer than our how long this same thing with text. So I'm going to turn this line line to a comment, and we will get the index array list 100. Okay, so our linked list took way longer than our array list. Our linked list took 7.5 million nanoseconds compared to our array linked list element, 190 billion elements, and do the same 963 is always of errors. Our linked million need to shift elements after elements to the left, down 500, and array resulting in nanosecond array list linked to array not this array level. This new listing array
Finding the right loan for higher studies is no walk in the park. It's a big decision to make. You get overwhelmed.
Describe the video. If you would like a copy of all this code, I will post this to the comment section. Hey, what's going on, everybody? It's your bro. Hope you're doing well. and in this video I'm going to describe the very basics of big O notation in, well, computer science. So sit back, relax, and enjoy the show. With big O notation is how code slows as data grows. It describes the performance of an algorithm as the amount of data increases, and really this notation is machine independent. What we're really focusing on is the number of steps to complete an algorithm, because some machines are going to run certain algorithms faster than others. And 3, we tend to ignore smaller operations. If we had some task that took n plus 1, we would just reduce it to just n because that plus 1 really isn't going to make a difference. So here's a few examples of big O notation. We have O of 1, O of n, O of log n, and O of n squared. And n is really just the amount of data that we're passing in. It's a variable like x. What we're focusing on is the performance of an algorithm as the amount of data increases, and n is a representation of the amount of data that we're passing in. Here's a more concrete example. I have a function named addup. We will add up to a certain number depending on what we pass in as an argument. The for loop within here will iterate once up to whatever number that n is, add I to sum, then return it. What if n was a large number like a million? Well, it's going to take just above a million steps to complete this function. This function is said to have a runtime complexity of O of n, linear time. As the amount of data increases, it's going to increase the amount of steps linearly or proportionally. Now, another way in which we could write the same function is to take sum equals n times n plus 1 divided by 2. We will get the exact same sum. So if n was, let's say, a million, this is still only going to take a couple steps, 3 steps. not a million steps. So this function is going to have a runtime complexity of O of 1. The input size doesn't matter. The amount of data that we have really doesn't matter. It's going to be completed in the same amount of steps. So this function is way better than this previous one. 3 steps is better than a million steps. And the reason that this isn't O of 3, because this takes 3 steps, is that we really don't care about smaller operations. In the grand scheme of things, they really won't make much of a difference. So we would just shorten this and say that this is O of 1 constant time. The input size doesn't matter. Here's a graph that I made to represent the different runtime complexities. We have data on the x-axis represented by n. So data will increase as we go more to the right, and we have time on the y-axis. I did add an asterisk next to time because some of these times can vary depending on what machine you're using, so these can vary. Another way to look at this is number of steps. So as we increase on the y-axis, these algorithms are going to perform with increasingly more time. They're going to get slower. So let's begin with O of 1 constant time. Anything that has a if you're starting at the beginning of a linked list. So O of 1 is time. One example videos, but anything that has a runtime complexity of O of log n will actually take, I don't want to say less and less time, but increasingly less time to complete. So as the data size increases, this algorithm is going to be more and more efficient compared to the early stages with a small data set. O of n is also known as linear time. As the amount of data increases, the time it takes to complete something will increase proportionally, linearly. That would include looping through the elements in an array and searching through a linked list. Next we have O of n log n, also known as quasi-linear time. This would include quicksort, merge sort, and heap sort. We'll talk about these concepts in future videos. So for the most part, this is very similar to linear time unless we're working with a large data set. Then anything using O of n log n is going to start to slow down when we work with larger data sets, hence this curve here. Then we have O of n squared, also known as quadratic time. A few examples would include insertion sort, selection sort, and bubble sort. As the amount of data increases, it's going to take increasingly more and more time to complete anything that has a runtime complexity of O of n squared. So just to compare linear time and quadratic time, with linear time, if our data set was 1,000 here, but if we were using so if our data set was 1,000, if we're using quadratic time, it's going to take 1,000,000 steps then, way more than linear time. So quadratic time is extremely slow with large data sets, but in the case of a small data set, it could actually be faster, as you can see by the graph here. And lastly, we have O of n factorial, also known as factorial time, and one place where this is used is with the traveling salesman problem, which I might discuss in a future video. So this is extremely slow. So if I had to give a letter grade to each of these runtime complexities when working with large data sets with constant time, this would be an A, like an A+. Logarithmic time would be a B, it's pretty good. Linear time is C, it's okay. Quasi-linear time is a D, it's just barely passing. Quadratic time would be an F, and factorial time, well, you get expelled from school. Although some of these runtime complexities are actually faster when working with a smaller dataset, so keep that in mind. Well, that's the very basics of Big O notation. It's notation used to describe the performance of an algorithm as the amount of data increases. So if you can, give this video a thumbs up, drop a random comment down below, and well, that's Big O notation in computer science.
In the next 60 seconds, I'm going to show you how you can get paid 1,500, 2,000, or even 3,000.
Alright everybody, linear searches. We need to talk about linear searches because this wouldn't be a complete course without them. With a linear search, we iterate through a collection one element at a time. The runtime number of a linear search is that they are slow for large data-sized datasets. And they don't need to be sorted. That's a huge benefit over some numbers. They don't necessarily integers. Int, array, and to make up some numbers, they don't necessarily need to be in order. All right, then let's find an index. Int index equals, and we will invoke a linear search function, which we still need to declare. We will pass in our array and some value we would like to search for. Let's search for the number 1. Okay, so then let's declare this function, create method, linear search, private static int linear search. So we have two parameters, an integer array, private. Okay, so then let's declare this function, create method, linear search, private static int linear search. So we have two parameters, an integer array and an integer. I'm going to rename I as value, so it's more descriptive. Okay, with a linear search, all we need to do is loop through our array one element at a time. So we can do that with the for loop. So let's set int I, our index, equal to 0. We will continue this as long as I is less than our array's length, then increment I by 1. What we're checking with an if statement is to see if our array at index of I is equal to the value that we're searching for, this parameter. If it is, then let's return whatever our index is, I. If we do not find it after iterating through our entire array, let's return -1 as a sentinel value. And that's all there is to it to our linear search function. So back within our main function, let's check to see if the value returned does not equal -1. That means that we found our value. So with an if-else statement, let's check to see if index does not equal -1. That means that we have found our element. So let's print element found at index plus index. Else, let's print element not found. System.out.println, element not found. So if we're searching for the number 1, we would find that at index 1, 0, 1. If we search for 5, that is found at index 8, 0, 1, 2, 3, 4, 5, 6. Seven, 8. If there's some number that's not in here like 10, then this will print element not found. So yeah, that's the idea behind a low for a large, and they do not need to be sorted. That's a copy of this code.
They're coming straight in. Trust me.
Well, and Rhythm in computer science. So sit back, relax, and enjoy the show. Alright, binary search. It's a search algorithm that finds the position of a target value within a sorted array or other collection. In order for a binary search to work, whatever we're searching through, it needs to be sorted. And basically what we do is we take half of the array and eliminate it during each step, and we will whittle down our collection until there is only one element remaining. In this example, I have an array of 11 elements. Each element contains a letter, and they're all sorted alphabetically. Let's say we are looking for the letter H and I need the index. What we would do with a binary search is that we always begin in the middle. We first check to see if our target value is equal to this middle value. If these are equal, then we can return this index, but odds are they're probably not going to be equal on the very first turn, the very first step. So these are not equal, then we will check to see if our target value is greater than or less than this middle value. Since H is greater than F, we can disregard this entire first half of our array, because since this is sorted, our target value could not possibly be within this first portion. And then we begin step 2, or phase 2. It's the same process as before. So again, we begin in the middle, check to see if our target value is equal to the middle value. They're not. Check to see if our target value is greater than or less than the middle value. This time H is less than I. We would delete the second half of this portion. We're not actually deleting these values, we're disregarding them. And then we can move on to step 3. We're repeating the same process as before. And this time these elements divide evenly, so we would just round down and begin and say that this is the middle. So H is greater than G. We would disregard this element, and we only have H remaining, so we would return this index because these values are equal. And that's a binary search. Now, a binary search isn't too efficient when working with small data sets. However, if you're working with a large data set like 1 million elements, well then a binary search is actually fantastic because we're eliminating half of the elements we are searching through during each phase or turn. So if we had 1 million elements after the first phase, we can already disregard like 500,000 elements, and then we just repeat the process until there's only one left. So if this was an iterative approach, we would need to search through these linearly, beginning with, index 0 and going all the way to 1 million. So a binary search is fantastic with large data sets. The runtime complexity of a binary search is O of log n. The larger the data set, a binary search becomes more search is O of log n. Data sets. The runtime complexity of a binary search is O of log n. The larger the dataset, a binary search becomes more and more efficient compared to other search algorithms. In a binary search method of arrays to begin with, and then later on we'll build our own binary search function. So we'll need an array to work with. Let's say we have an array of integers named array. Int array, and the size of this array will be 100. We'll increase the size later for demonstration purposes, and we'll need a target value that we're searching for. I'll just name this target. Int target equals, what about 42? We'll search for the number 42, and we'll need to populate our array. So we can do so using a for loop. Int I equals 0. We will continue this for loop as long as I is less than array.length, and increment I by 1 during each iteration. Then we will fill array at index I with whatever I is, our index. Okay, so the cheap way of using a binary search is to use the built-in binary search method of arrays. Let's say int index equals arrays dot binary search. And taking a look at this binary search method, there's 2 arguments that we have to pass in, an array and whatever we're searching for. So we will pass in our array and our target, then return the index. And let's display that. So let's check to see if our index is equal to -1. If our target is not found, then that means -1 will be returned from our binary search method. So let's print something. System.out.println. What about element not found? Actually, better yet, target not found. Let me change that. Target plus not found. Okay, then else. Else, we will display system.out.println element found at colon space plus index. All right, let's try it. Okay, element found at 42. Cool. Now let's create our own binary search function for practice. I'll turn this line into a comment, copy it, paste it, and get rid of this erase portion. Okay, then I'm just going to use a shortcut to generate this function. Okay, then I'm just going to use a shortcut to generate this function. Okay, so private static int binary search, there are two parameters, an array of integers named array, and int target. So we'll return -1. That acts as a sentinel value. -1 means that the value is not found. Now what we'll need at this point is the beginning and ending index of our array. So let's say int low will be the beginning, and int high is the end. Array.length -1. So we have a low index and high index. And we'll create a while loop. While low is less than or equal to high, we'll continue this while loop and keep on searching through our array. So first we need the middle index. Int middle, and here's the formula for that. Low plus high minus low divided by 2. So we have our middle index. We will take int value equals our array at index of middle. So this will extract that value found within this element. Okay, so this portion is optional. I'm just going to display whatever this value is so we can count the amount of steps it's going to take to find a value. So let's say middle colon space, whatever this value is. This line of code is optional. I'm just doing this for educational purposes. Okay, now we need to check to see if our value is less than or greater than our target or equal to. If value is less than our target, low equals middle plus one. And actually, I'm going to get rid of these curly braces. If you have an if statement and you only have like one line of code, you don't really need the curly braces. I'm just doing this so it's easier to read. Okay, else if value is greater than target, we will set our high index. High equals middle minus 1. Else, that means we have found our target. Else, return middle. So this means that target is found. And by returning -1, that means target not found. And that is our binary search function. Let's try it. Okay, element found at 42. So it took us, let's see, 1, 2, 3, 4. 4 steps to find the number 42 within this array of 100 elements. Now let's increase the size because binary searches do extremely well with large data sets. So let's say we have 1 million elements, and let's change this target. What about 700? And well, with 100 target not found. by returning -1. That means target not found. Found at 42, so it took us, let's see, 1, 2, 3, 4. 4 steps to find the number 42 within this array of 100 elements. Now let's increase the size because binary searches do extremely well with large data sets. So let's say we have 1 million elements, and let's change this target. What about 777,000, whatever that number is? Okay, so let's search for it, and let's count the steps. So there's quite a number of steps here, but let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 steps. Now imagine if we took a linear approach where we began at index 0 and looped through this entire array looking for this index. And in that case, looping through an array would have a runtime complexity of O of n. To find this number, it's going to take over 700,000 steps because we're iterating once for each element within this array, compared to a binary search where it only took 20 steps. Well then, in conclusion, a binary search is a search algorithm that finds the position of a target value within a sorted array. Half of the array is eliminated during each step or phase. So that's a binary search algorithm. If you would like a copy of all this code, of course I will post this to the comment section down below, and that is the binary search algorithm in computer science.
That client review was brutal.
We're gonna be underwater for weeks.
I'm already so pruny.
This is fixable. Just use Grammarly.
Alright, what's going on everybody? Interpolation searches, these are an improvement over binary searches that are best used for uniformly distributed data. Basically,
taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I will want you. You right. You right. Tonight, hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me. But baby, if you leave, you don't have to worry. I will want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's it's hard to believe. I'll give you what you need, and baby, we can be what you want. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you want. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you want. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you want. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. We're all. You right. We're all. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. We're all. You right. We're all. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. We're all. You right. We're all. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. We're all. You right. We're all. Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you. You right. You right. Taking you to Malibu tonight. Hop in, baby, we can take a ride. Give you what you dream of. With me inside, you lose control. It's not what it seems on the low. Baby, don't worry what you don't know. Give you what you dream of. Give you what you dream of. I know it's hard to believe. I'll give you what you need, and baby, we can be what you wanna. And it's alright with me, but baby, if you leave, you don't have to worry. I want you.